Okay, so have you ever noticed, like with these really powerful AI models, they can be kind of all over the place sometimes, like
Yeah.
with how much they seem to be thinking, you know what I mean?
Right.
It's like some of them just go on and on, explaining everything in excruciating detail, and then others, they give you this really quick answer, and you're like, wait a minute, did you even really understand the problem?
Yeah. It's like they didn't even try, you know?
Exactly. And it makes you wonder, like, how much of that is just wasted effort? Like,
Hmm.
are they just spinning their wheels computationally, or are they actually getting to the core of the issue?
Right. Because you want them to be smart, but you also want them to be efficient, right?
Totally. And that's what we're diving into today. It's not about how to get these advanced language models to reason for just the right amount of time, not too much, not too little.
Yeah, think about it. Like, if you're using AI to solve problems for you, you kind of want it to show its work, right?
Oh,
So you
absolutely.
can see how it got there, but at the same time, you don't want it to take forever.
Right. You don't want to be sitting there twiddling your thumbs waiting for it to finish.
Exactly. And that's where this whole idea of controlling the reasoning length comes in. Imagine being able to tell the AI not just what you want it to do, but also how much effort it should put into figuring it out.
Right. Like giving it a budget almost.
Exactly, a computational
I
budget.
love that.
And to really get to the nitty-gritty of this, we're going to be looking at a paper
Oh,
called
God.
Controlling How Long a Reasoning Model Thinks with Reinforcement Learning.
Catchy title.
It is. It's by Pranjal Aggarwal and Welleck. They're both from Carnegie Mellon University,
Awesome.
and they're really tackling this problem head on.
Nice. So, what's our mission today then?
All right, so our mission today is to unpack the proposed solution, which is called Length Controlled Policy Optimization, or LCPO for short.
ACPO. Got it.
And we're going to get a little academic here. We're going to dive into the formulas they use to actually implement this precise control over reasoning length.
Okay. Love it.
So if you're curious about how we can actually govern the thinking process of AI, you're in the right place.
All right, so let's start with the basics. What is the problem that Aggarwal and Welleck are trying to solve with this whole uncontrolled reasoning like thing?
Okay, so the main issue they're addressing is that right now these advanced reasoning models, they generate what are called chain of thought sequences,
Okay,
which is basically the step-by-step reasoning process they use to get to an answer.
like showing their work.
Exactly, showing their work. And the problem is the length of these sequences, it's all over the place.
Ah, I see.
It varies a lot and it's really unpredictable. And to quote their paper directly, they say the length of their reasoning is uncontrolled, making it impossible to allocate a test time compute budget to achieve a target performance level.
So basically, you don't know how much computational power you're going to need to get an answer?
Ex and that makes it really hard to manage resources, right?
Yeah, totally. So how does that play out in the real? I mean, what are the actual consequences of this?
Okay, well, imagine you have a model and it's trying to solve a relatively simple problem, but it ends up generating this huge chain of thought, like tens of thousands of tokens long,
Oh, wow.
which is a ton of computation. It's basically wasting a lot of power and money.
Right, like it's overthinking a simple problem.
Exactly. Overthinking it. And then on the flip side, you might have a really complex problem
Okay,
and the model just stops reasoning too early.
like it gives up.
Yeah, kind of like it gives up before it's really explored all the possibilities, and then you end up with an answer that's just wrong or incomplete.
Right, and that's a problem.
Yeah, it's unreliable and it makes it hard to use these models in a practical way.
Absolutely. I mean, especially if you're thinking about like real world applications where you need consistent and efficient performance,
Exactly.
this unpredictability is a huge obstacle.
It is, and that's where length-controlled policy optimization comes in.
CPO.
Yeah, LCPO. So how do they actually try to fix this well?
Yeah, how do they actually try to fix this?
They introduced this method called length-controlled policy optimization, or
Okay.
LCPO, and it's based on reinforcement learning.
So for our listeners who might not be familiar, can you give us like a quick explanation of what reinforcement learning is?
Sure. So, in a nutshell, reinforcement learning is training an agent,
Okay.
which in this case is our language model, to make a series of decisions by giving it feedback in the form of rewards or penalties.
Got it. So it's like training a dog, you give it a treat when it does something good.
Exactly. It learns by trial and error based on the feedback it gets. And with LCPO, they've set up two main objectives that they want the model to achieve.
All right, come on me. What are those objectives?
Okay, so the first one is pretty straightforward. It's the correctness of the final output.
Makes sense. The model still needs to get the right answer.
Exactly. We still want it to be accurate. The second objective, that's where the real magic happens.
Okay.
This is all about making sure the model's reasoning process.
That chain of thought.
Yes, that chain of thought, it has to stick to a certain length limit that's given in the prompt.
So you're basically telling the AI, show your work, but keep it concise.
Precisely, you're setting a limit on how much it can ramble on, and here's how they describe it in their paper.
Okay.
LCPO trains models to satisfy two objectives, and I'm quoting here: one, correctness of the final output, and two, generating reasoning sequences that meet a length constraint specified in the prompt.
Got it. So it's not just about the what anymore. It's also about the how much.
Yeah, you're controlling the process now, not just the outcome.
That's pretty cool.
It's a pretty big shift in how we're interacting with models.
It seems like it would have some really big implications for like efficiency and resource management.
Oh, absolutely. We'll get into that more later.
Okay, but for now, can we talk about this L1 model that they mentioned in the paper? What is that
All
exactly?
right, so L1, that's the actual reasoning model that they built and trained using their LCPO method.
Okay.
It's a model with 1.5 billion parameters, which is a lot, but it's built upon a foundation model called Quen-distilled-R1-1.5b.
So L1 is like the finished product of applying the LCPO training.
Exactly, and here's the interesting part. They actually created two versions of L1 Exact and L1 Max.
Okay, so what's the difference between these two?
It all comes down to how strictly they follow that length constraint that we talked about.
Okay.
So L1 Exact, it's trained to generate reasoning sequences that are as close as possible to the target length that you specify in the prompt.
So it's trying to hit that exactly.
Exactly on the nose. L1 Max, on the other hand,
Okay.
it's trained to make sure its reasoning sequence is no longer than the target length.
So it's like a cap.
Yes, exactly. It's a cap. It can be shorter, but it can't go over.
And what's really cool is that with these L1 models, you can actually control the trade-off between accuracy and computational cost just by changing that length constraint in the prompt.
Yeah, they have this great visual in the paper that shows how you can smoothly adjust the model's performance based on how many tokens it's allowed to use.
It's really impressive the level of control they've achieved.
It is. All right, so are you ready to dive into the formulas now?
Let's do it. This is where it gets really interesting.
All right, so let's start with LCPO exact reward function.
Perfect.
This is how they actually train the model to hit that exact target length. Okay. Formula, and it might look a little intimidating at first, but we're going to break it down step by step. Don't worry.
Okay.
So it looks like this RY exog equals IRY exog. Izog egol.
All right, so let's take it slow. What does that R at the beginning stand for?
So they R stand for reward.
Okay.
And in reinforcement learning, the whole goal is to train the model, take actions that maximize its rewards over time.
So it's like giving it a treat when it does something good.
Exactly. The higher the reward, the better the model is doing.
Got it. So what about those Y and I terms? What are those all about?
Okay, so Y, that represents the actual output that the model generates,
Okay.
which includes both the chain of thought and the final answer it comes up with, and I gold, that represents the correct answer, the one we want the model to produce.
So Y is what the model actually spits out, and I gold is the ideal answer.
That's it exactly.
All right, and I'm guessing those angold and 9 terms have something to do with the length.
You got angold is the target length, and tokens that we specify in the prompt as the desired length for the reasoning process.
Okay.
And night, that's the actual length in tokens of the output that the model generates.
So it's like the actual versus the expected.
Precisely. Now that next part, that y equals all goal, that might look a bit weird.
It does a little bit.
It's called the indicator function,
Okay.
and it basically acts like a switch. It evaluates to 1 if the generated output y is exactly the same as the correct answer to goal.
Okay.
And it evaluates to 0 if they're different. So the model only gets a positive reward if it gets the answer completely right.
Got it. It's all or nothing.
Exactly. And then we come to the last part of the equation, that a 9 gold there.
Okay, what's going on there?
All right, so that part is all about controlling the length. The norm gold then, that calculates the absolute difference between the target length and the actual generated length.
So how far off it is from the goal.
Exactly. And we use the absolute value because we want to penalize the model, whether it's too long or too short.
Makes sense.
And then that difference is multiplied by alpha.
Okay, so what does alpha do?
Alpha is a really important part. It's what's called a hyperparameter.
Okay.
And it's basically a value that we can adjust to control how much weight we give to correctness versus length adherence.
So a lower alpha means we care more about getting the right answer.
Exactly. And a higher alpha means we're more focused on sticking to the length constraint.
So it's like a balancing act.
It is. We can tune alpha to find the sweet spot between accuracy and efficiency.
Got it. So that reward function for LCPO exact, it's not just about encouraging the model to get the right answer and stay within the length limit.
Right.
It's also about making the reasoning more concise, especially when we give it a short target length.
Exactly. It's incentivized to be efficient with its thinking.
That's pretty clever.
Okay, now are you ready for the L1 max reward function?
Hit me with it.
Okay, so remember, L1 max is all about setting a maximum length.
Right. It can be shorter, but not longer.
Exactly. So the reward function changes a bit to reflect that here's what it looks like. RY eggold equals I gold, clips this day, plus ludi 01.
Okay, so we see some familiar terms, but also some new ones. What's that clip function all about?
All right, so the clip function, it basically just limits a value to range.
Okay.
In this case, it means that Whatever is calculated inside those parentheses,
Hmm.
it's going to be forced to be between 0 and 1.
So it keeps the value within a reasonable range.
Exactly. It helps with the stability of the training process.
And what about the stuff inside the parentheses, plus ACE and EP?
Okay, so we still have alpha, our trusty balancing scalar, and then we have in Goldling.
Which is the difference between the target length and the actual length.
Right, but notice it's not the absolute difference anymore.
Because with L1 max, we only care if it goes over the limit.
Exactly. And then we have that plus delta.
What does delta do?
Delta is set to 0.5 in their setup, and it basically introduces a soft constraint on the maximum length.
Okay, what does that mean, a soft constraint?
It means that even if the model goes a little bit over the target length,
Hmm.
it won't be penalized too harshly as long as it still gets the answer right.
So it's a bit more forgiving.
Yeah, it allows for a little bit of wiggle room, which again helps with training.
I see. So it's like a balance between strictness and flexibility.
Precisely. And the paper mentions that L1 Max actually uses both reward functions depending on what's specified in the prompt.
Interesting. So it can adapt to different situations.
Yeah, if the prompt asks for an exact length, it uses the LCPO exact reward function. But if it just specifies a maximum length, it switches to this modified version with the clip.
That's pretty cool. So it's like a 2-in-1 model.
Exactly. All right, so now that we've gone through all the math.
Yeah, my brain is a little fried,
I know it's a lot to take in.
but it's fascinating.
It is. Okay, so let's talk about the actual results. What did they find when they tested these L1 models?
Yeah, did it actually work?
So they trained these models on a massive math reasoning data set.
Okay.
And then they tested them on a whole bunch of different benchmarks, including not just math, but also things like logical reasoning and general knowledge.
So good mix of challenges.
Yeah, they really put it through its paces, and the results were pretty impressive.
Okay, tell me more.
So one of the biggest findings was that L1 significantly outperformed previous for controlling reasoning length, especially on those really difficult math problems.
Wow, by
Some cases, they saw relative gains of 100 to 150%.
that's huge.
It is, and they also had significant absolute improvements, particularly when they limited the token budget to 512 or 1024 tokens.
So it was more efficient too.
Yeah, they think this is because L1 is able to adapt its reasoning process to fit within that constraint.
Instead of just cutting it off prematurely.
Exactly. Those older methods, they would just translate the reasoning, which obviously leads to worse accuracy.
Right, it's like interrupting someone in the middle of a thought.
Exactly. You're not going to get the full picture. And they also found this really interesting pattern with L1's performance.
Okay, what's that?
So as you increase the token budget, the performance also increases, but it does so in this log linear way.
Okay, I'm not familiar with that term.
So basically it means that there's diminishing returns. As you add more tokens, the performance gains start to slow down.
I see. So it's not like a straight line up.
Right. But the interesting thing is that L1 scaled much more efficiently at lower token ranges compared to other models.
So it's getting more bang for its buck, so to speak.
Exactly. And then they also looked at how well L1 actually followed those length constraints.
Yeah, did it actually stay within the limits?
Yes, it did, and it was really precise, especially on the math tasks. The average deviation from the target length was only about 3%.
Wow, that's pretty good.
It is, and even though the error was a bit higher on those out-of-domain tasks, it's still a huge improvement over having no control at all.
It's a step in the right direction for sure.
Absolutely. Now, this next finding is where things get really interesting.
Okay, I'm intrigued. Lay it on.
So they call this the shortcut capability.
Shortcut, okay.
And what they found was that even though L1 was trained to handle these potentially really long reasoning chains,
Hmm.
it actually performed exceptionally well even when they gave it very short prompts.
Wow, so it's like a sprinter who can also run a marathon.
Yeah, exactly. It's versatile and it's efficient. And get this, when they gave it the same limited token budget, L1 actually outperformed not only its base model,
Okay.
but also much larger models like GPT-400 on those short reasoning tasks.
No way, that's crazy.
I know it's a smaller model, but it was more effective.
So it's not just about controlling the length for efficiency, it's also about making the reasoning better, even when it's short.
Right. And this has some really big implications for using AI in situations where resources are limited.
Like on a mobile device or something?
Exactly. You need quick and accurate answers without using up a ton of processing power.
So how do they think this is happening? Why is L1 so good at short reasoning, even though it was trained for longer chains?
So they did some analysis of the keywords that L1 used in its reasoning process.
Okay, what did they find?
They looked at how often it used terms related to self-correction, exploring alternative solutions, setting up the context of the problem, and drawing conclusions.
Interesting. So they're looking at the language itself to understand how it's thinking.
Exactly. And what they noticed was that in longer reasoning chains, L1 tended to use more keywords related to self-correction and verification.
Like it was double checking its work.
Right, and it also used stronger language when it came to drawing conclusions.
So it was more confident.
Exactly, but the interesting thing was that the frequency of keywords related to exploring different solutions, it didn't really increase with length.
So it wasn't just trying every possible approach, it was being more selective.
Yeah, it seems like it was able to focus its efforts more effectively, and overall, it suggests that giving the model more tokens allows it to be more thorough and build a stronger case for its answer.
Like it has more time to think things through.
Right, and they also found that the ratio of thinking tokens to solution tokens stayed pretty consistent across different lengths.
What does that mean?
So basically, it means that the model is scaling its reasoning appropriately. It's not getting bogged down in unnecessary details when it comes to presenting the final answer.
So it's concise but thorough.
Exactly. Now, one last thing I wanted to mention is that they addressed this concern about the model just memorizing answers.
Oh yeah, that's an important point. How do you know it's actually reasoning and not just regurgitating stuff it's seen before?
Right. So to test this, they evaluated L1 on a newer version of a math competition dataset called AME 2025.
Okay.
And this dataset contained problems that L1 had never seen during training.
So it was brand new information.
Exactly. And what they found was that L1 actually performed better on the seen dataset compared to other models, including those much larger ones.
So it was able to generalize its knowledge.
Exactly, which suggests that it's not just memorizing answers, it's actually learning how to reason and apply that reasoning to new problems.
That's really impressive.
It is a big step forward in terms of robust and reliable AI.
So to sum it all up, it seems like LCPO and this L1 model are a pretty big deal.
Yeah, I'd say so. It's a new way to manage and optimize how these advanced language models approach reasoning.
It's like giving them a set of guidelines to follow, but in a way that actually improves their performance.
Right, and the results speak for themselves, the impressive accuracy, the generalization capabilities, and that surprising effectiveness in short reasoning scenarios.
Yeah, that was a big one.
It all points toward a future where we have much more fine-grained control over how AI thinks.
Which is both exciting and a little bit scary.
Definitely both, but mostly exciting, I think.
So for our listeners, what are the key takeaways from all of this?
Well, I think the biggest one is that we're making some real progress in controlling the length of AI reasoning using techniques like LCPO.
Right.
We can now prompt these models to think for a specific amount of time, which opens up a whole new level of control over computational cost and performance.
And maybe even more importantly, we're learning that training models for controlled reasoning can actually make them better at those quick and concise answers too.
Exactly. It's not just about limiting their thinking, it's about making them smarter overall.
So this brings us to a pretty thought-provoking question for all of you listening out there.
I love a good thought-provoking question.
Me too. So now that we have this ability to control AI reasoning, what are the potential implications for different fields?
Right. What could we do with that?
Imagine applications where managing resources is super important, or where you need different levels of reasoning depth for different types of problems.
Yeah, and what other innovations do you think we'll see in this area, especially when it comes to dynamically adjusting the reasoning length based on how complex the task is?
It's really mind-blowing to think about how this could change the way we interact with and utilize AI.
Definitely. And if you're interested in diving deeper into this, the original research paper, Controlling How Long a Reasoning Model Thinks with Reinforcement Learning, has a ton more detail and examples.
Yeah, it's a great read even if you're not a math whiz.
Totally.
Okay, well, that's all the time we have for today. Thanks for joining us for this deep dive into the world of controlled AI reasoning.
It's been a pleasure.
Until next time, stay curious.
And keep exploring.